share my screen. All right. Can all of you see the screen and hear me clearly?
Yes, sir.
Yes, sir.
Yeah. Okay, great. So we have been discussing some of the popular financial models, their characteristic function and SDEs. In particular, we started discussing the mean reverting process last week. So the Ornstein-Uhlenbeck type processes, and one particularly important example that we discussed last class is the Vasicek's model, which has certain nice properties along with the advantage that it has explicit functional form for the characteristic function, which means empirically, computationally, we are in a good position. So today we will start our discussion with the Cox-Ingersoll-Ross model, which is a modification of Vasicek model, and it's the same kind of modification as in the Heston model, that I want to prevent the interest rate from becoming negative. We discussed that even though Vasicek is quite nice, the problem is the interest rate can become negative. There is no preventive measure. Just like in the Heston model, we will now discuss the Cox-Ingersoll-Ross model, which prevents the interest rate from becoming negative. But before I start, are there any questions or clarifications from whatever we have done so far? Because several of these models are quite empirically or theoretically complicated. So unless you are following, it will become progressively more difficult. After a point, we will stop discussing the models and then start discussing the empirical implementation, different strategies. So if the theory part is not clear, later on it will become very confusing. Okay. And again, I will expect you to read the book. I have uploaded the set of problems I want you to do from the exercises of Ali Hirsa, as well as a few other problems collected in a problem set. So this is not the right screen where Bangladesh is batting badly, but where I want to go is here. So I'm loading the computational finance classroom page, and I have uploaded the problem set yesterday evening. So you should be able to see this set of problems here that I have numbered, as well as these extra problems in a doc file, which is of course in the Google Drive. So can all of you access this? Has anyone checked?
Yes, sir.
Yes, sir.
So these will be our primary target in the course, solving these problems. Some of them are, of course, computational in the sense that they will require coding, programming, simulation, and other numerical analysis or using computers. Most of these are algebraic. Okay. So now let me resume the class. So today we will talk about 2-3 very important models in computational finance, in finance in general, not only computation. These are 2 or 3 of the most popular models in finance. And of course, our focus will be on the characteristic function, so that later on we can get into the computation part of it. So as I said, today's discussion begins with the Cox-Ingersoll-Ross model. Cox-Ingersoll-Ross model is a modification of Vasicek, and the modification is proposed to prevent the interest rate from becoming negative. So it is the same idea as in Heston. In Heston, we did the same thing to prevent the volatility from becoming negative. Here, the target is to prevent interest rate from becoming negative. Similar trick, we add a square root of R term to the volatility part of it, of the SDE. So the mean reverting process, as before, is now augmented with this kind of a volatility term. So the change of short rate, DR, the generating equation for the short rate, is given by a mean reverting trend, which as usual is this kappa eta minus RT dt plus lambda times square root of RT theta. And this square root term is what will prevent it from becoming negative. Lambda is a constant rate. So lambda is the volatility of the time change. So this you should contrast with the original Vasicek formulation. So this was the original Vasicek formulation. So we started out with this Ornstein-Uhlenbeck type processes. There were no corrections here. So there was no guarantee that interest rate will always remain positive. In the Cox-Ingersoll-Ross variation, the CIR variation, what we are doing is we are adding this square root term here to make that correction with the usual notation. So now the notation is quite familiar, so we need not repeat it again. So what is the characteristic function? So similar to the Vasicek model, again, we are interested in the realized interest rate. So we are actually interested in the integral of RU du, which is the realized interest rate from time 0 to time t. So any time interval. And again, doing some tedious algebra, it can be shown that the characteristic function for the realized interest rate, capital R, is given by this expression. So this is A e to the power B times R0 of this type, where A and B are given by these two particular functions. So obviously these functions are coming from our earlier discussions of developing characteristic functions, just like we did in the local volatility models. You can see some of these examples here, particularly the Heston model, because in spirit, we are doing a similar thing as in the Heston model, where what we did for DVT in the Heston model is what we are now doing for DRT. So that formulation helps here also. And if you do the algebra, we will see that the characteristic function for the CIR model is given by this expression A e to the power BR0, where A and B are of this type. So again, we will not be focusing on the derivations in particular. So there is no compulsion for you to go through this algebra. But of course, the details are available in the book and in the references cited. So if you are curious, you can look at it. So that's one part, the characteristic equation. We have the SDE. We are able to derive the characteristic function. So the last piece would be to be able to compute the term structure. As before, as for the Vasicek model, we also did the term structure for the Vasicek model in this equation 1.30. Again, for the CIR model, we are interested in the same object, the term structure, which we will be needing to price the bonds. And again, the expression will be of the same type. This 131 is exactly similar type as 1.30, where this expectation of e to the power minus RT can be derived from this characteristic function again by the same insertion as before. Okay, so this I think is pretty much clear how we are approaching it. Of course, the algebra might be complicated. I'm not saying that the algebra is simple or straightforward. It is neither, but the approach is quite straightforward. We are modifying the standard Vasicek model, the standard mean reverting process, with a Heston type modification, we are able to derive the characteristic function in this certain form. And then from that, because we are interested primarily in term structures, we are also able to compute the term structure capital P. So this is our typical mean reverting process formulation, both in the Fuzzy-Check form and also in the CIR form. CIR form has the additional advantage that it can prevent interest rates from becoming negative. Okay, so that's our first model today. Moving on, now let me talk about another very important model, which is the variance gamma model. But before we talk about the model, let us discuss a little bit about why do we need this model and why am I so excited about the model. Variance gamma model is really, really important, and there is a very good reason for it. So far, the models that we have seen in this chapter, in chapter 1, all the models talked about handling the volatility and the drift in a smooth manner. So they all had nice small rates of change, which you can represent through a differential. And then you make marginal modifications to impose some realistic conditions or to realize some nice assumptions. But they are in general smooth type of models. We model volatility, we model the drift. The drift may be mean reverting. The volatility may also be mean reverting. But in general, in real life financial data for prices, returns, rates, we often see non-smooth behavior. We have already seen some graphs earlier, and we will be seeing more graphs as we go along for prices and returns and interest rates, exchange rates, that movements are not always very smooth. We often see jumps. We often see upward or downward jumps in the prices or rates. So it is imperative that we talk about models which can accommodate such jumps. And obviously, our favorite model in this case would be the Poisson type arrival processes. First of all, they are theoretically quite nice. We know how to do the algebra and the maths of it. That's one reason. But the more important reason is that actually Poisson type jump models have some very desirable properties which match with our empirical experience. So we start our discussion in this direction with for the price jumps, modeling price jumps with this Poisson type jumps. So what we do is we talk about a Poisson type jump diffusion model. It's still a diffusion model, but we incorporate Poisson type jumps there. And that's how the variance gamma process will be defined. Formally, the variance gamma process is a pure jump process that accounts for high activity. So high activity means it can have infinite number of jumps in any finite time interval. So things can happen very frequently, very fast. And this is in keeping with the normal distribution. So if you understand the spirit of the normal distribution, there also we see that there might be many changes in any finite interval of time. Only now the nature of the change is different. We are not talking about the frequency. The frequency is as before. We are now focusing on the nature of the change. So is this distinction clear? Do you understand what I am talking about? So yes, in order to motivate the variance gamma model or any jump type models, the logic is that we see non-smooth behavior. There could be jumps, and we could also see a lot of jumps. many jumps happening in a short interval of time. So here, what we are trying to model, what the modeling approach is to accommodate infinitely many jumps in any finite interval of time. And I
Sir,
say,
I have a question.
yes, of course.
So, in the first lecture of the last semester, you showed that if there is a sudden jump in the change in the stock market, then the exchange actually enters and do some regulations and has some margin so that it does not vary too much from that position.
Yeah.
So, but then how can it be like in a very short time there are more than 2 jumps or 3 jumps?
Okay, good.
Because
Very
if
good
there is
question.
fast jump, the regulation takes place.
Okay, that's a very good question. Let me talk you through this rest of this paragraph because the answer is here in this paragraph. Yeah, just
Okay, sir.
hold on to the question for a minute because the answer is here when I talk about it, but it's good that you have raised this issue so I can connect these two things together. All right. So as I said, the variance gamma model with the Poisson type jumps accommodates infinite number of jumps in a finite interval of time. And that's where the regulator's role may come in, but just hold on to it. Let me finish the description first. Now, we are also saying that unlike other jump models, there are many other type of jump models. At least in this variance gamma process, it is not necessary to introduce a diffusion component separately for the PG process. Why it is not necessary? Because the Black-Scholes model is already a special case of this process. So as we define the process below, we will see the definition, the SDE for the process below. We will see that the Black-Scholes model, the original simple diffusion model, is already a special case. And this high rate of activity is already accounted for through that model. But this high rate of activity has to be qualified in a certain way, because otherwise the regulators will come and stop us. So what is this automatic regulation that is built into the model? So this is the important qualifier. One can show that unlike the normal diffusion where the variance increases without bounds linearly in time, the sum of absolute log price changes is finite for the variance gamma process. So the variance gamma process is defined in such a way that it has finite variation. If you remember the quadratic variation definition from last semester, this is the same thing, same concept. And variance gamma has built-in finite variation condition. So even though I may have a lot of jumps in a short interval of time, theoretically infinitely many jumps in a short interval of time, their total impact on the market is finite. It is bounded. And that is why the regulator really does not need to come in, because the regulator, so the clause that we discussed last term was that if the change is above a certain percentage, then the regulator comes in. In the variance gamma process, the usual jumps that are generated could be very frequent, but they are typically of a reasonably small order because the sum total has to be finite. So it is highly likely that even though we see many jumps, the individual magnitude of a particular jump will not exceed our threshold. So the regulator's role might not be necessary most of it. So this finite quadratic variation in theoretical terms translates to the real life regulator's cutoff not being breached very often. So the regulator's cutoff, which is typically 5% or 10% of the current state, that is rarely breached. So that makes us more confident about using the variance gamma model and theoretically allowing for infinitely many jumps. Subhrajyoti, is this okay?
Yes, sir.
So this is what we discussed. We discussed in passing last term. I don't remember exactly when, but we talked about this finite quadratic variation thing and the problem that happens for the usual Black-Scholes model. Remember that we could not define the derivative.
Yes, sir.
So the variance gamma model, even though it is more complicated, it is allowing jumps, it is actually built in finite quadratic variation feature, and that helps it to keep the movements, individual movements, typically at a small magnitude. So variance gamma has finite variation, and then we have the Levy type argument to show that it can be written as the difference of two increasing processes. So when we have a jump process, some upward, some downward, and if it is sufficiently well behaved, then it can be written as a difference of two increasing processes. This is, of course, a very important theorem in stochastic processes, which we are using. So what we are saying is that instead of looking at the jumps as a whole, let us look at the positive jumps as one process, which would explain all the price increases, and look at all the negative jumps, downward jumps as another process, which would explain all the price decreases. In other words, you can think of a good news jump process and a bad news jump process. And since both can come in at any random time, our realized jump process would be a sum of these two things. Part of it explained by good news, the remaining explained by bad news. And this is the theoretical characterization that we are going to use. So in the case of the VG process, the variance gamma process, the two increasing processes, both are increasing process, they are subtracted to obtain the VG process. And we will see that actually these increasing processes are themselves gamma processes. So let us now look at the differential equation. So is this explanation clear? Because this is sort of a longish paragraph, lot of English, but I wanted to put it in as a whole, as in HITSA, because this gives you the whole story and also tells you about the connection with the real market. So is this clear to all of you? Because this is important. This is not just a description which you ignore. This is actually the important mathematical feature that we are going to summarize in the equations coming up. Because if this paragraph is clear to you, then this generating stochastic differential equation will be easier to understand. So, okay, so interpreting the silence to my convenience, let me start talking about the differential equation. So the SDE for the variance gamma process is a 3-parameter generalization of a Brownian motion. So it starts with the Brownian motion, but then it augments it in a certain way. How does it do it? So let me first look at the first equation. I have this simple generating function B defined with T sigma theta. So theta is the drift and sigma is the volatility, simply as theta T plus sigma WT. This is exactly as in the Black-Scholes model, in the original diffusion process model. Now, how do I introduce the gamma processes here. The way to introduce the gamma process is done through evaluating this Brownian motion, which has a constant drift and a constant volatility. So far very standard, but we evaluate it at a random time change. And this random time change is generated by a gamma process. So what do? We say that our actual process X, the realized process X, which is defined by at time t by these three parameters. So this new parameter will come in apart from sigma and theta. What is happening to X? Ax is evaluated, X is B. X is B function as in Bt sigma theta, but evaluated at a random time point, which is given by this gamma process at time t with unit expectation and a finite constant variance. So this is the trick. So the time scale has now become random. So the changes that happen does not happen linearly in time, happens at random points of time generated by a gamma process. So my T index, both here and here, has now become random. So it's a random variable. So the final generating equation for the variance gamma process is given by theta gamma plus sigma W evaluated at gamma. So when I look at successive changes, the changes are no longer linear because the difference has become random. So is this clear? At least conceptually, is this clear?
Yes, sir.
I'm talking about the generating process, the underlying generating process, which is a gamma process. And you know why we are choosing gamma process, because that is consistent with our Poisson arrival processes. So the inter-arrival times are exponential, so that we are modeling with a gamma process. So both the trend, theta t, and the Brownian motion in the volatility part, Wt, are actually operating on a random time scale. So my generating equation now involves this gamma random variable in place of time subscript t. So what is the typical explanation for this? So each unit of calendar time is the linear time t. So basically each unit of calendar time is now viewed as having an economically relevant time length. So what is this economically relevant word? So economically relevant time length is given by an independent random variable which brings in some economically meaningful news. So it's the arrival of economically meaningful news. So time as in and of itself is not the important point to us. So today, tomorrow, day after tomorrow is not how we want to see time. We want to see time in terms of event time, where economically relevant events are taking place. And this event arrival process is approximated by a gamma distribution. So what we do is we take a gamma density function with mean 1, unit mean, and some positive variance mu, which is this notation, this piece of notation here. And that now dictates our final generating process X. So thus, we can view this model as accounting for different levels of trading activity during different time periods. Sometimes there will be a lot of arrivals in a short time. That means the market is more active. When market is more active, it is as if time is moving faster. And at some other point of time, on some other day, when the market is slow, when we say market is slow, that means there are fewer events happening, fewer economic events happening. So as if time has become slower. So to distinguish between the two periods, we do not say that, okay, today we had many trades and tomorrow we had few trades. we will say that today we had many economic events happening which speeded up the time process. And tomorrow we had fewer economic events happening which slowed down the time process. It sounds slightly artificial, but that is precisely the generating principle of the differential equation you can see on the screen now. All right. So again, I am repeating these verbal descriptions again and again because I think, I do believe that these explanations are very important. The mathematics of it is definitely important, but the explanation is equally important because unless you know what you are dealing with, the mathematics will become a very mechanical process. So continuing with our generating equation discussion, how do we model the stock price? We normally model the log stock price. So under the variance gamma model, our unit period continuously compounded return, the return distribution is still normal because we have this generating WT here. Once we do the compounded return, it will still be normally distributed, but conditional on the realization of a random process. Because as I said, our timeline has now become random. So I do not know whether you have done some stochastic process with random termination. Are those things discussed at all in your stochastic process courses?
No, sir.
Or counting processes? Counting processes where the inter-arrival times are random? Is that familiar? Because I thought that such models are very much discussed in Ross. I don't know whether Ross was your textbook. Can anybody tell me whether these are familiar? So I can hear a lot of silence. But can anyone clarify whether those things are at all familiar to you?
Sir, those of us who did, who spent our first year in Delhi, stochastic process was not part of our course actually. So whatever stochastic process we did, it was part of some other courses like that.
It doesn't matter which course it was in. What I am asking is, are you familiar with this kind of objects or models?
Oh, no.
It could be part of some epidemiology topic, could be part of demography. It need not necessarily be called stochastic process. It could be called something else. But the issue here is, I have random inter-arrival times. There is an arrival process, and I am basically counting number of events.
So for extreme counting processes, the counting process was there in the syllabus as some as a renewal process and under the biggest renewal process, but random termination, that thing was not.
Achha. Okay, fine. So even without random termination, we are still fine. So you have counting process. At least some of you have been exposed to the renewal process model. So renewal process is a very good example, very convenient example for this. So this is what we are now talking about. So we are talking about economic events happening at random time points, and those economic events are driving the stock price. The X process is basically evolving according to those economic events. So the returns also depend on these random events. Correct. But once we condition on these event realizations, once we condition on this counting, then the conditional distribution is same as our typical Brownian motion model. Because if I condition on gamma, then I just have t here, t and omega, t and wt. So then the return will again be normally distributed, conditional on the arrivals. Is that clear to all of you? Those of you who have done renewal process before, I think this would be very easy to understand, but intuitively, even without a formal stochastic process example in your head, is this logic clear? So I guess I'm particularly asking the Delhi students, students who were studying in Delhi in the first year, who did not have a formal stochastic process course. Is this intuitively clear to you, what I am talking about? I don't mind discussing this more, explaining it again, but I need a response.
Can you repeat this again?
So our economic events are happening at random times, and those economic events are driving the price process or the return process, whichever you are trying to model. So the returns are not being realized linearly with time. They are being realized randomly as the economic events happen. So prima facie, I do not know how the distribution of the return would look like because of this random arrival thing. But now suppose you condition on the arrivals. So it's as if I have told you about the future time points where these arrivals will happen. If you know when these news events are going to happen, conditional on that, now your return process will look the same as the original diffusion process in the Black-Scholes model. Because now t has become deterministic. I have conditioned on those t time points. So if there are some t1, t2, t3, 3 events, and I have already told you what is t1, t2, t3, then the remaining is exactly as in the Black-Scholes model, because there are no more randomness in the time scale. And hence I argue that the return will be conditionally normally distributed. Is that clear?
Yes.
So that's the starting point. So you see, this is a trick that we have been using in our probability classes since our undergraduate days, that sometimes finding expectation of a random variable might be very complicated because the probability distribution is very complex. So what we do is we try to simplify matters by conditioning that random variable on another random variable. So instead of finding expectation of x, we try to find expectation of x given y, where y is a related, cleverly chosen random variable, so that given y, expectation of x can be evaluated easily. Once I'm able to do that, now it becomes a function of y only, and then it might be possible to integrate out y and find the unconditional expectation. Integrate or sum, whichever, depending on the context. You all have done this before, right?
Yes, sir.
So this is a trick that we have been using many times. So that is the same trick we are going to use here. We know that the variance gamma process has a random timeline, which would be extremely complicated to handle directly. So what do? We first condition on the events. So then the timeline becomes fixed. Once the timeline is fixed, then the returns are normally distributed because the model is known to us. So that's what we do here. So we say that under the variance gamma model, the continuously compounded return is normally distributed, conditional on the realization of a random process. And this random process is basically the random time which has a gamma density. So conditional on that gamma density, I know what I am going to get. And that's how we will evaluate the whole process. So the resulting process and the associated pricing model will give us a 3-parameter generalization of the standard Brownian motion. Remember, this is the standard Brownian motion model. But we have a 3-parameter generalization where this additional parameter came because we had this gamma distributed time, gamma distributed arrivals. So summing up, I say that the log of the asset price, which we typically model under the VG, is given by log ST equal to log S0, which is obviously the time zero value. That's the usual starting point. R minus Q, rate of interest, dividend, plus omega. Remember, this is our mean correction, which we will evaluate shortly. This is our mean correction. So this is the trend part. And then the volatility part is directly modeled by this X. The volatility part is directly modeled by this X, or equivalently, I can put everything in the exponential form and say that ST is S0 times e power R minus Q plus omega t plus X. And of course, omega has to be fixed, omega has to be calibrated so that under the risk neutral model, expectation of ST equals the bank rate, the riskless return. This is our usual logic. So we use the risk neutral measure logic to fix the mean correction. This we will do. But the important part will be here, where direct evaluation of this expression will not be possible. We will first need to condition on the arrival, evaluate the conditional expectation, and then integrate out. The density of the log asset price under the variance gamma model at time t can be expressed conditional on the realization of gamma time change G. So let us use the symbol small g for the gamma density. So we'll condition on small g. Conditional on the realization of gamma time change G as a normal density function. So the density, the conditional density will be a normal density, phi. And then we will find the unconditional density, as I said, by integrating out G. That will be our strategy for the evaluation. So this is the density part. So the density denoted by small f for X. X is of course capital X. So small x, 3 parameters, will be given by integration of the normal density function. This small phi is our typical notation for normal density. This should have been theta t and sigma square t in the Black-Scholes model. But of course, now I have to replace it with the random time change. So I say theta g, sigma square g. And then I have to integrate out g. So I insert the gamma density here for g and I integrate. So this is our conditioning and then integrating out strategy of evaluating expectation. And if I write out the gamma density, this will be the expression. So this expression doesn't look very simple, but it can be analytically handled, certainly numerically handled. That we will do shortly. But before we get into the evaluation part, let us point out a few of the advantages. So this generalization of the model allows for the parameters to not only control the volatility of the Brownian motion, because earlier all we had in our control was how much volatility and how much trend. That's it. The rest of it was perfectly normal distribution. But now this is no longer exactly normal distribution. Unconditionally, it is not normal at all. So what are the additional advantages I get using this 3-parameter model? It can be shown that this model also allows for fat-tailedness or kurtosis, as in a symmetric increase in the left and right tail probabilities. So this is called thick tails. So larger kurtosis would mean tails are fatter. So both on the right and left extremities, there is more mass than would be allowed in a normal distribution. That's one feature. The second feature is this can also accommodate asymmetry in the sense of skewness. It can allow the left or the right tail to be heavier, longer than the other. So this variance gamma formulation can also accommodate excess kurtosis and skewness compared to normal distribution where both are frozen at the ideal. And if you look at this density carefully, one can also find out that the variance gamma has the log normal density as a special situation, and of course the Black-Scholes formula as a special case. So I can also generate the log normal type density from here, and certainly I can generate Black-Scholes. That would be trivial because we have been augmenting Black-Scholes to generate this. All right, so far?
Yes, sir.
So variance gamma, we have discussed how it is generated. What are the economic implications of that? What are the probabilistic implications of that? In particular, some of the distributional properties, kurtosis and skewness, that can be allowed in the variance gamma formulation, unlike the standard normal distribution. Okay, so now let us spend a little bit of time on the evaluation part of it. In particular, we want to evaluate the characteristic function. Okay, the first step is easy. If I condition on G, first condition on the time, gamma time arrival, I know it has to be normal distribution, so I know the characteristic function. So I know that the conditional expectation here for x, e to the power I u x has to be of this form, e to the power I u theta plus I u square sigma square by 2 times G. Because that is what we get from the normal distribution, conditional on G. G itself is a random variable. Now I integrate. To integrate over G, this is what we do. To get the final characteristic function, unconditional characteristic function of xt, I have to find the expectation of this conditional characteristic function, expectation over G, which will be given by the gamma density integral. All right, looks ugly enough, but note that this is again in the gamma integral class. So this is, if you just collect terms, one can show that this is the characteristic function of a gamma distribution with shape parameter t by nu and scale parameter nu, but evaluated at not u, but at u theta plus I u square sigma square by 2. So whatever can be put here inside the bracket. If I take I common and G common, if you look at the e to the power terms here, let me magnify a little bit. So these two e to the power terms can be collected together. Ig can be taken out, and what I will get inside is this much. So basically the evaluation is happening at a different point. So in effect, this expectation here has to be of the same form as the gamma characteristic function evaluated at a different point. And if you can recall the gamma characteristic function, which I will scroll up and show you, because that's where we started. I think gamma was the first model that we discussed. This is the form of the characteristic function. 112. So now if I scroll down, the same form should happen with a different calibration for the variance gamma model. And this 1.32 is what we should have. Actually, what we should have is 1 by nu here, but then I can multiply by nu throughout and make it look simpler. So is that clear? So I am using the normal characteristic function first with conditioning. I know the form. Then I integrate out. So when I integrate out, I can recognize this new the integrand inside again as a gamma type function. So I again know the form of the characteristic function with a different argument. That's what I insert, and I simplify it a little bit. So with these two simple tricks, without actually evaluating integrals, I can find the variance gamma characteristic function. So finally, the characteristic function of the variance gamma process with parameters sigma, nu, and theta at time t, unconditional, is given by this expression. It's the same expression as this one, just rewritten. So is this clear?
Yes, sir.
So this is one of the most important models which accommodates jumps in financial asset price theory, along with normal inverse Gaussian, and I think these two are the most popular. Normal inverse Gaussian and CGMY. We will discuss normal inverse Gaussian and CGMY both today, but these three are the top three candidates in terms of popularity. And you can very easily see why, because variance gamma is starting out from a very complex setting, having jump processes, infinite activity, and everything. But it uses only 3 parameters, so it's a very parsimonious model. Not only that, the mathematical complexity is quite low, because I am able to use all the existing results smartly to derive the generating characteristic function and explicitly evaluate it in 2-3 steps. So of course, later on in the subsequent chapters, we will talk about derivative pricing under variance gamma model, and we will use both analytical like transformation methods as well as numerical like simulation methods. But one comment can be quickly made right now is that if I want to price the European option, the simple European option under the variance gamma model, it should be very easy to do so. Because again, what do I do is first condition on the random time. Once I condition on the random time, it becomes a simple European option pricing model in the Black-Scholes variety. So I know the expression for it. Then the final variance gamma European option price is obtained by integrating the gamma density out. So the final strategy would be to evaluate an European option price, capital C, let's say call option. I put in the Black-Scholes price here, conditioning on G, fixing G, and then I integrate over the whole gamma density of G. This is numerically quite straightforward. And this kind of power we have obtained because we have this kind of conditional nice distributions, conditional normal distribution. And again, when I uncondition it, I get back the original gamma form. So mathematical complexity is reduced a lot. It is built in there, but directly you can use some ready-made results. And if you look at the original Levy formulation and the Levy-Khinchin theorem that we discussed last week, let me just go back here. This was the original Levy process characteristic function formulation. Remember, we said that this is often becomes quite complicated when we take up specific models, specific d nu models. So variance gamma is one such specific model because it has jumps. So it will also fall under the purview of this Levy-Khinchin family. And what one can show is the following. Let me scroll down again. What one can show is, if I want to put it in the Levy-Khinchin family, the Levy measure for the variance gamma process, the d nu process, can be written as this thing. So I can write d nu x as kx dx, where the kx function is precisely given by this form. So it has the positive news model and the negative news model. So this lambda p is the positive news rate intensity, and lambda n is the negative news intensity. So you see, this is for x greater than 0 and this is for x less than 0. Adding these two up, I have the Levy measure for the variance gamma process. And of course, lambda p and lambda n, the intensities can also be explicitly computed under this model. Of course, it will involve theta, sigma, and mu. But explicit evaluation is possible for the Levy-Khinchin representation of the variance gamma model, where I can explicitly write out the density function d nu. So whenever we talk about the Levy representation, we have this general integral, but for some of these particular cases, we can write out the specific density involved. Okay, so let's take a break. I have overshot the first period, but we will make the second one shorter. So let us take a break for 15 minutes and we will restart at 11:50. So I'll start recording and share my screen. So again, Bangladesh. Fine. So variance gamma process, the one that we discussed this morning. So are there any questions on that? Because it's a very important example, not only in itself, but also to understand the subsequent models, because there is a certain pattern to this discussion. So variance gamma sort of sets that pattern. So are there any questions or clarifications at this point? No questions. Okay. So then let me move on to the next model, because we have discussed the variance gamma model. It's generating stochastic differential equation, characteristic equation, as well as, fortunately, the explicit Levy measure for the variance gamma process. So empirically, we are all set if we are going to handle variance gamma. So the next big model, big name, is CGMY. CGMY is very similar in nature, so I will not discuss it in much detail, excepting the fact that CGMY is after 4 persons. So C, G, M, and Y, these are 4 researchers who developed this model together. And in the process, the parameters in the model are also called C, G, M, and Y. So when you see my screen, the CGMY model, it has these 4 parameters, C, G, M, and Y. And The paper had these 4 authors, also C, G, M, and Y. So you should find it out yourself because that's the reference given here. One of them happens to be an Indian, at least a person of Indian origin. Okay, so CGMY model attempts to accommodate both pure diffusion, like in the Black-Scholes, and pure jump, as in the variance gamma. So it is basically a super model built on the, which has a separate pure diffusion part. So to go straight to the Levy process for this CGMY model, again, d nu x is defined as kx dx. I have an explicit density, and kx is given by this positive news component and this negative news component. Here, unlike the variance gamma process, where there was only an intensity here and a linear term in the denominator, now you have a power law in the denominator. And that power law is dictated by this parameter, capital Y. So if I put capital Y equal to 0, then it will look like the variance gamma model. And also the exponential part in the numerator, lambda p and lambda n, they are in this model now called G and M. So I have G and M in the exponential part, C as in the constant that puts an weightage on the positive news. So I can give more weight on the positive news or less depending on C. And the power law in the denominator is controlled by the parameter capital Y, which is less than 2. So that's the CGMY process. It accommodates both, as we claim, both pure diffusion and pure jump. But the explicit generating equation is very hard to derive, and CGMY is known only through its characteristic function. So this is where implicit formulations start coming up. The CGMY model, we only know through its characteristic function, and that characteristic function, of course, is computed explicitly in this form. So this is the form of the CGMY characteristic function. Similar tricks, similar generating processes. So you can find the details in the book, but suffices to understand the differences between these models. So I'm not going to discuss it in length. We have the Levy measure, explicit Levy measure, calibrated by the 4 parameters, and we have the characteristic function, which comes in this form, where again this C, Y, M, and G parameters appear. Okay, so as I said, there were 3 very popular models: variance gamma, CGMY, and normal inverse Gaussian. So our third candidate for discussion today is normal inverse Gaussian. And this is again due to Barndorf-Nielsen. We discussed Barndorf-Nielsen last term in that special lecture. It is a pure jump Levy process, but it is now with infinite variation. So if I want to accommodate infinite variation, variance gamma is not suitable because we made it nice, making it finite variation. Normal inverse Gaussian, on the other hand, accommodates infinite variation. So obviously, there will be some disadvantages, like not having an explicit density, but the characteristic function again can be explicitly shown. The parameters of the NIG process are again named sigma, nu, and theta, and the characteristic function is given by this particular form. So again, to summarize, in empirical work, these three equations, variance gamma, which we discussed in detail, and the other two, CGMY and NIG, normal inverse Gaussian, these three are the most popular models. And now you can see that for different situations, one of these would be very appropriate. So we discussed one of them in detail. The other two, I just mentioned the characteristic function and the Levy measure here. But you can always find more details. And in fact, when you get into the empirical chapters later on, we will be doing illustrations. We will be looking at illustrations with one of these three models quite often. So let me then move on and discuss another variation of the variance gamma model. Because the variance gamma is somehow a very interesting object. It's a very interesting object. So this particular variation of the variance gamma model is of interest in itself. So what does it do different from variance gamma? So variance gamma with stochastic arrival, VGSA model. So what is this stochastic arrival thing? Variance gamma model has stochastic volatility, certainly, because I do have this intensity of the volatility here. But what it does not have is it cannot explain volatility clustering. Because I have that constant sigma there, I cannot explain volatility clustering with the variance gamma model. We discussed last week that variance clustering is a very common phenomenon in financial time series, prices, returns, exchange rates, etc. So this model, VGSA model, is an attempt to allow for clustering along with the other variance gamma features. The other variance gamma features are attractive, so we want to retain them. In addition, we want to have the volatility clustering feature. So VGSA is constructed by taking the variance gamma process, which is homogeneous Levy, and we build in a stochastic volatility by evaluating it at a continuous time change using the CIR model. So we want to build in stochastic volatility, and that is done through the integral of a CIR process. So what is happening is the time change or instantaneous time change is now represented by a integral of a CIR process. The instantaneous time change is represented by the CIR process. So the time change overall, realized time change, is an integrated CIR process. And of course, remember that CIR has the mean reversion feature, and that mean reversion feature in turn makes the volatility clustering phenomenon a part of this model. So again, I will repeat. So we have this variance gamma with stochastic arrival model to do what? I have the variance gamma process to begin with, but it's an homogeneous Levy process. We include a time change process using the CIR. So how do we do it? We say that the instantaneous time change follows a CIR process. So the realized time change process will be an integral of the CIR process. And because CIR has mean reversion, that mean reversion will lead to clustering. So let me first take a look at the differential equation, how it is created, and then we will try to understand what it is actually doing, because the description may not be so clear. Okay, So the CIR process, let's recall that if yt is having the CIR process, then the generating equation will be dyt equal to kappa eta minus y dt lambda square root y dw. So this is the mean reversion and this is the prevention of negative values. That's our CIR. And CIR is supposed to be the instantaneous time change. So the time change process will be given by an integral of the CIR process. So time change will be given by capital Y, where capital Y is integral of Y from 0 to t. Then I can write out the SDE of the log price, a log of the market variable, as in the VG process. So I will use the same generating equation as the variance gamma process. So let me go back and connect. I have the same generating equation as in the variance gamma process, but our volatility time change will be dictated by this capital Y. So this capital Y will get inserted in the time change process. And then you can actually evaluate the characteristic function. So we start with the CIR, the instantaneous time change, to evaluate the characteristic function of capital Y. So capital Y has this characteristic function. Phi evaluated at ut y0. Y0 is the starting time, kappa, eta, and lambda. Kappa, eta, and lambda are part of this model, of course. So this is our characteristic function for capital Y, which I can write out as capital A e to the power b y. That we have done before for CIR. This was the expressions. Then the VGSA process, the actual VGSA process, is defined how? It is defined by VG at capital Y. So VGSA is VG at capital Y. So the time scale is now dictated by capital Y. Remember earlier in variance gamma, we had an independent gamma process that generated the time scale. Now the time scale is dictated by the integrated CIR process. So in total, I will need 6 parameters to define the process, because I will need 3 additionally for the CIR process, this kappa, eta, and lambda. These 3 additional parameters for the CIR process, and sigma, nu, theta for the original VG process. So 6 parameters in all. The characteristic function, if you do same kind of work, it can be written as phi of minus I, capital psi of VG at U. So this is the characteristic function for VG, psi VG. This we know from before. 1 by nu intensity, and this kappa, eta, and lambda are all coming from the CIR process. So again, let me go back and recall. So what I do is, I want to introduce clustering in volatility. How can I do that? I know that the Cox-Ingersoll-Ross model has this clustering feature through its mean reverting equations. Because it had mean reverting equations, it has clustering features. So what I do is, I incorporate a CIR modulated time change. So my time change is dictated by the CIR in the variance gamma process. So when I include that time change in the variance gamma process, I call it VG with stochastic arrival. So what will happen to the characteristic function is, the characteristic function will be related to the variance gamma process, but it will be moderated by a different timeline. So this capital psi log characteristic function of the variance gamma process we have seen before. it looks like this. Then we define to arrive at the final characteristic function, what we do is we define the asset process like this. So instead of the log scale, we write it as st equal to s0 times the numerator here as e to the power r minus qt plus zt, and the numerator is our expectation of zt. So this is the mean adjustment. This is the omega term. Remember, we always did the mean correction through the omega term, which we write out explicitly here in the denominator. To first evaluate e to the power zt, e to the power zt is of this form here. So we write that phi with all this. And remember that this power has come. I'm sorry, I made a mistake. This should be the expectation part. I'm sorry. My bad. This is the denominator. The expectation is this, where I have inserted minus I in place of u. This is our old trick. The same trick that we have been using over and over again for the mean correction term, that I insert minus I in place of u. So here I had the expression u. So I introduce minus I in place of u, and this is what I used to get. So I can write this expectation term in the denominator here, and the original characteristic function as given by this equation in the numerator here, and I can write the full characteristic function of the log price for the VGSA process as this. So I write IU log ST because that is what I am interested in, the log ST value, and that will be given by, this is the part that has come out, IU log S naught R minus QT from here, times the e to the power ZT part, this characteristic function, and the expectation part, which is below. So collecting everything together, we do have a closed form expression for the VG with stochastic arrival characteristic function for the log asset price. Because most of the time we will be working with the log price. So now let me go back to the description and see whether it really makes sense and what we have actually done matches with what we claim to do. So the VGSA model was constructed to allow for volatility clustering. So how did we incorporate the clustering? We introduced the CIR process, the mean reverting CIR process, which allows for clustering. Where did we introduce it? In the time scale, because that's how the clustering will happen. When things happen quickly, I have clustering. So that's what the mean reversion process will force. So what is happening here? We take the original CIR process generating equation, look at its integral version, because that will be our realized time change scale. And I put it. So, and for that, I do have the characteristic function again for capital Y that we know how to do. But then I put it in the variance gamma process time argument. So to create the VGSA, I put the capital Y term in the VG time argument. And that's how we arrive at the characteristic function of the whole process. And then once I do the mean correction, I can also evaluate the characteristic function of the log price process in this manner. So that's the complete expression for the variance gamma with stochastic arrival. It has got more parameters, 6 parameters actually. So it would be harder to calibrate, will require more data. But the advantage over variance gamma would be that it can also explain volatility clustering. But having said that, as I have already mentioned before, that variance gamma with NIG and CGMOI, these three happens to be the most popular models in financial crisis. So even though VGSA has this additional interesting feature, it is not so common empirically. First of all, there are more parameters to estimate. That's one point. The other point is it is technically much more hard to handle. VG is technically easier to handle in that sense. So any questions so far? Because we have actually gone through a large number of models in this chapter already, starting with the basic gamma exponential normal distributions. We have actually moved on to quite a few popular generating processes, variance gamma, CGMOI, the basic Levy process. And then we also talked about the variance gamma with stochastic arrivals. So collecting them together is the basic toolbox of the computational finance expert. Of course, we are not done because we have only talked about the theoretical expressions. We will move on to computation in the later chapters, but more or less, this is the spectrum of the tools that are commonly used. So even though many of these expressions are quite complicated, the derivations are pretty much tedious, but we will not focus much on that. But we do need to be familiar with these expressions. I'm not saying that you need to memorize these expressions, but you need to be familiar in the sense that which part means what. That should be clear to you. Which part is the variance gamma generating process, which part is the clustering, which part is the the mean reversion. All these intuitive clarity must be there. Also the Vasicek model, which is our starting point of mean reversion models for interest rates. So when we take up the computational topics later, chapter 2 onwards, we will have these models again and again. We will be using one of these models as our canonical model and apply it and demonstrate the empirical methods. So it is very, very important that you familiarize yourself with these models. Yes, Prakhar, you have a question. Oh, no, okay. Achha. Anyone has a question? Can you all listen to me, hear me actually? Now I am...
Yes, sir. Yes, sir, we can hear you.
You can hear me, okay. So well, all right. So I would really like you now to read these models in detail from the book because I am not discussing all the details. The algebraic details you need not memorize really because I'm not going to test you on that. But as I said, the interpretation of the various components of the model and particularly the generating equation logic, that has to be absolutely clear because only then you will understand why a particular model is applicable or appropriate in a particular context. So it's not a mechanical exercise. The final models look algebraically complicated, certainly, but they have been arrived at from very clear-cut financial logic, not only mathematical logic. So that is what I am asking you again and again to study, to read out. All right, so if there are no questions, then I will talk a little bit about our main agenda in the course, because our main agenda was derivative valuation. And like last term, most of the time our focus will be on risk neutral measures. In fact, almost all the time, our focus will be on risk neutral measures. The only time when we will not be able to talk about risk neutral measures will be when the market is incomplete and we have non-uniqueness in the risk neutral measure. So whenever we have incompleteness in the market, we know that there are multiple risk neutral measures possible. So then we will have to talk about something else, some other strategies. But most of the time, complete markets, we want to value derivatives. So we want to use the risk neutral measure. So how does it go? So pricing under the risk neutral measure, this is just, again, this is a recap of what we did last term. But I thought that doing this recap is useful because it will familiarize you with the notation, because some notations are slightly different from Pliska or Oxendal. So we will quickly go through this. If there are clarifications required, you have to ask me. So the most general expression of risk neutral pricing for a derivative whose payoff depends only on the terminal price. So these are European type things. So let's start with the simple ones, only on the terminal price. So there is no path dependence as of now. Of course, later on we will do that. So how is it stated? So S, capital S at T is our time T price of the security, which is the terminal time. F is our risk neutral density, and F capital T will be the risk neutral density of the terminal time stock price. Of course, conditional on the initial stock price. This is the information we have now. We are interested in some derivative. So suppose V of S capital T is the payoff of that derivative at maturity. So at maturity, our payoff is capital V. So we want to find the price of that derivative, which is C capital T. So C capital T is the price of a T maturity derivative with payoff V, where the stock price will become S capital T at time T. Of course, for risk neutral pricing, our pricing equation will be, CT will be e to the power minus RT, expectation of VST under the risk neutral measure Q. So Q is, as usual, our risk neutral measure, which we have to deduce expectation of the value discounted to current time. That will be the price of the derivative. That's the definition. And we can rewrite it using the density, because we have already assumed that we have the risk neutral density. So it's an integral over the whole real line, VF ds. Again, simplest example that you can think of is the European code. So that will be something that we will be using all the time. Now, often we need to do a change of the probability measure. We have seen this in the discrete setup from Pliska, the dp/dq kind of adjustment in the continuous setup from Oxendal. And we called it the Radon-Nikodym derivative. So that's what we are looking at again. So suppose MT is a strictly positive Q martingale. So MT is a martingale under Q probability, strictly positive, and expectation equal to 1. So MT is a particular type of martingale. It's a Q martingale with expectation 1, and it is strictly positive. So if I want to evaluate the probability of any set A, then what I will do is I will evaluate it in this way. I will compute the expectation under Q of MT and the indicator of A. So far so good, which I will write out in the density form, because I assume that there is a density for Q, MT omega indicator, which will be an integral over the set A, MT dq. That's the formulaic expression for a probability. Now, suppose I am interested in the expectation of some random variable x under probability p, which is xdp. Now, if am is my dp dq, so m is actually the Radon-Nikodym derivative, then I can do a change of probability measure and say that expectation under p of x is same as expectation of mx under q. Again, in discrete setup, this is very simple to write, but in continuous setup also, we do have the Radon-Nikodym formulation and the Girsanov's theorem that we talked about last term. What does it give us? So this is the result that explains how to switch between Q and P when we are taking conditional expectations. So suppose we are interested in time t expectation of x under probability P, then that I can write in this form, introduce this dpdq both in the denominator, both in the numerator and in the denominator, using the fact that expectation of this is 1. So I can always divide anything by 1, no problem. So this expectation will be same as this Q expectation by MT, given that MT is a Q martingale. Okay. So this is something that we will be using all the time. And I will stop here for today. We will continue on Friday on the rest of this chapter, and we will start chapter 2. So Friday, so let me stop sharing now. Friday, we are going to start chapter 2, which is the transformation techniques, the Fourier transform and its empirical counterpart. So I suggest that you do take a quick look at the initial sections of chapter 2, but more importantly, study chapter 1 in its entirety. And you also have the problem set now in your drive. Start working on the problems. So any questions at this point? So I have asked you to do 3 things. Read chapter 1 now, because we have almost done with chapter 1. We will move on to chapter 2. So at least familiarize yourself with the game plan of chapter 2, what chapter 2 is going to do. And third, now start on the chapter 1 problems. And I have given you the problem set. Okay. So